Dark matter is kind of frustrating. We see evidence for it everywhere we look, from the rotation curves of galaxies to the cosmic microwave background. And all attempts to explain it away as some quirk of gravity fail. Whatever dark matter is, it must be cold, collisionless, and abundant. We'd like to know what dark matter is made of because it can help us understand the dynamics of galaxies and the evolution of the universe. Oh, and by the way, it is by far the most common particle in the universe, so it'd be nice to know what it's actually made of. Let's say you're on a small boat in the middle of the ocean, or it could be a big boat, it doesn't really matter for this metaphor. Anyway, it's the middle of the night and you see lights on a distant shore. Now those lights tell you that the shore exists, but it doesn't tell you anything about it. There could be mountains or jungles, you just don't know. This is the situation with dark matter. The luminous material in our universe, the stars and galaxies, tell us that dark matter exists, but it doesn't tell us what it's made of. Now, taken together, there's so much evidence for dark matter. I could spend the rest of this episode going over all the evidence. I mean, I wrote a book about it. And check this out. There's the rotation curves of galaxies. There's the temperatures of galaxy clusters. There's the bending of light around massive structures. There's the large-scale structure of the universe itself. There's the cosmic microwave background. It goes on and on and on and on. We know that dark matter exists, but we don't know what it is. But we do know what it isn't. It's not just normal matter that happens to be dim and hard to see, like rocks or planets or black holes. We know this because we've made measurements of the very early universe that tell us how much normal matter is in the universe, and there simply isn't enough to account for all the gravitational effects. Instead, dark matter has to be cold and collisionless. Cold means that the dark matter moves slowly compared to the speed of light. And collisionless means that it doesn't interact with itself or normal matter. That means dark matter is everywhere. Dark matter particles are streaming through this room right now. We are swimming in an ocean of dark matter particles. But because the dark matter doesn't interact with normal matter, we can't directly detect it. We can only learn about it through indirect methods. There are some things we do know about dark matter, but to tell you, I need to go to the chalkboard. Let me show you one of the pieces of evidence that we have for dark matter. And I want to show you this because it's more than just using this evidence to infer that dark matter exists. We can also figure out how it acts in our universe. And to do that, we're going to look at rotation curves. So rotation curves are a connection between the velocity of stars in orbit around a galaxy and the amount of stuff, the luminous matter that we can see in that galaxy. This is basic Newtonian mechanics. It's just simple gravity. Yep, thanks, Isaac. So check this out. When we look at a galaxy like this, most of the material is actually compressed into the core. And then the further away you get from the center, it thins out. And so if we make a plot of the velocity of stars versus the distance, it should look something like this. There's more stuff in the center, so the stars orbit faster and faster, but then it starts to thin out and you get further away. And eventually, the most distant stars should not be orbiting very quickly at all. This is not what we observe at all. Instead, we see something completely different in galaxies across the universe. It goes up like this, and then it stays up. The stars in galaxies are orbiting the center much faster than they should be if we just accounted for all the luminous matter. There is something else going on. There is some invisible kind of matter. There is dark matter. Let me show you something cool. Shoot, I'm out of room. Is this one of those fancy chalkboards that spin up? It is. All right. What we've discovered about dark matter is that every single galaxy in the universe is surrounded by a ball of it, something we call a halo. And that every halo in the universe shares a common structure, a common shape, something we call a universal density profile. This one that I'm about to show you, by the way, is called the NFW profile for Navarro, Frank, and White, the three astronomers who figured it out. And the equation looks something like this. It tells us that all dark matter, its density as a function of radius, looks like a scale density divided by the radius over a scale radius times 1 plus radius over scale radius squared. This scale density and scale radius are different numbers for every single halo, but no matter what, they all share this common shape. And the shape looks like this. Density is a function of radius, starts like this, and then goes down. And the scale radius tells us where this breaking point is. It tells us something interesting about the evolution of dark matter halos. It tells us that they first form with a central ball of density and then slowly over time accumulate more dark matter particles. This is amazing. This is telling us about the history of structure in our own universe. But this is all theory. Let's see what experiments can possibly tell us about dark matter. That's how we know dark matter behaves theoretically. But what we really care about is directly detecting it. We can see its gravitational influence everywhere in the universe, but we want to know it, we want to feel it, we want to taste it, we want to smell it. I mean, this aquarium has normal matter in it. Not too much, but enough. But really, it's full to the brim of dark matter. We just can't see it, but let's pretend that we can. Oh, perfect. Thank you. Right. Look at all that dark matter. Dark matter makes up 80 to 90% of all the mass in every single galaxy. We just can't directly see it. We want to know how dark matter interacts with itself and with the normal or baryonic world. That's where every single theorist with time to kill makes up their own pet theory of how dark matter might work. And we have so many candidates. We have, weakly interacting massive particles. We have a self-interacting dark matter. We have axions and axion-like particles. We have primordial black holes and sterile neutrinos, and on and on and on. But what really matters is that all these different ideas, all these different theories predict how dark matter might behave in our universe. And then we can go out and try to detect it, observe it, somehow catch a glimpse of dark matter and prove one of these hypotheses right. And there's all sorts of possibilities of how dark matter might interact. So, for example, two dark matter particles may occasionally collide and annihilate each other in a flash of gamma ray energy that we can see. Or it could be that dark matter buries itself deep in the heart of a star and raises the temperature higher than what you might normally expect. We might even detect it here on the Earth. We could set up, say, a cryogenic ultra cold detector and wait a really long time. And then occasionally a dark matter particle will hit the detector and heat it up just a little bit, and we can detect that heat. Or we can set up really pure xenon or argon and again, wait a really long time, and dark matter comes in and releases a flash of light that we can see. We have dozens of detectors and instruments and observatories around the world hunting for dark matter every single second of every single day. We just haven't seen any yet. Sorry about that. It can get a little bit frustrating. I mean, does dark matter even exist? Luckily, I know an expert.
I'm Jana Levin. I'm a professor of physics and astronomy at Barnard College of Columbia University.
In our episode on dark matter, we're covering some of the possibilities, some of the candidates of what the dark matter particle could be. What is the difference between, say, a WIMP and like an axion or one of the ultralight bosons? How are these particles different, and where in our theories do they come from?
Well, the first thing I want to say is that we know that dark matter exists, even if we can't explain the bulk of it. The problem isn't whether or not dark matter exists. We see neutrinos, and they are dark matter. We know that there are particles that do not interact with light, and they have mass, and they contribute to the weight of the universe, but they're not sufficient to explain the bulk of it. The surprising part isn't that there are particles that don't interact with light. The surprising part is that it's so hefty. We account for some kind of 5% residual ashy residue left over from the Big Bang, and the dark matter is more like 27%. And that's the bizarre part that we don't understand. So we have definitely seen dark particles. It's kind of thrilling for a theoretical physicist to think that it's a hint to something beyond what we already know. And that's what dark matter is giving us almost as a gift. What we don't know. It's giving us a clue.
It's a gift. Why can't the neutrinos be the dark matter? Why is that ruled out?
It's a great question, because neutrinos are absolutely a physical, undeniable, verifiable example of dark matter. They do not interact with light. They have all the properties of dark matter, but they're not heavy enough or abundant enough to explain the extreme dominance in the energy pie. So if you think of the energy pie of the universe, dark matter is taking up like some 25%, let's just say roughly. The neutrinos that we know about are not hefty enough to make up for that pie, but they're definitely an undeniable example of dark matter. So I think the question is really, are there really heavy neutrinos? And that's basically, a lot of people are looking for that. They're looking for WIMPs, weakly interactive massive particles, WIMPs, which is what neutrinos are. They're weakly interactive massive particles, and they're looking for WIMPs that are much, much heavier than neutrinos and that don't fit into our standard understanding of particle physics.
Does dark matter do more than just sit there and gravitate? Did it potentially play a role in the very early universe? I'm thinking like baryogenesis and matter-antimatter asymmetry and all the crazy physics happening in the first few seconds of the Big Bang. Could it be that dark matter played a role back then too?
I mean, that's a really great question. I think when we're searching for dark matter, we're cross-correlating with explanations of the baryon asymmetry. When the universe was created, in principle, if all the symmetries exist, there should be an equal amount of matter and antimatter, and they should annihilate and there'd be nothing. And so we know that there's a violation of that symmetry. We know that for some reason matter is preferred over antimatter, and so there's a tiny, tiny excess. Should dark matter play a role in that? Probably. One would hope so by the economy of explanations. But we don't really know. So like if we find the dark matter, for sure the hope is that we're going to be like, whoa, does it explain baryogenesis? And where does it fit into the bigger scheme? And, all of these things are like clues nudging us towards the right explanation. It's almost too ambitious to try to grope for it all at once. Like we're lucky if we find one thing. And that thing will definitely redirect other searches.
Jenna, thank you so much for your time and joining us on this episode. As you can see, when it comes to dark matter, there are more questions than answers. Is dark matter simple, consisting of just a single kind of particle? Or is it complex with lots of different kinds of particles participating? Is there still some undiscovered theory of gravity beyond Einstein's relativity that could just explain away all these results? Not now, Albert. Are there new forces of nature involved? What role did dark matter play in the earliest moments of the universe? Dark matter is more than a hypothesis. It's a framework for understanding vast swaths of phenomena across the universe. But it's like a house that isn't finished. We have the foundation, we just can't live in it yet. And that's why dark matter is on the edge of knowledge.